of the Motivic geometry seminar. We are very pleased to have Tom Bachmann talk about the eta-periodic Motivic stable homotopy theory. Please, Tom.
Okay, well, thank you very much for the invitation. Let's see if I can do something useful. So throughout S is always going to denote some scheme. And I mean, eventually we're going to specialize down to fields maybe at the end. But for now, we can think of pretty much anything. And so let me try to remind you. So I'm gonna more or less assume that you have some idea what this means, right? So Motivic stable homotopy theory, okay, maybe you agree on that. So let me, I'm sure you also know what eta-periodic means, but just for the sake of it, let me remind you what these letters mean. So there's this important construction called, well, the half map. And what you do, well, you just take the affine plane over your base, whatever, and then you remove the zero section. All right, let me just write this. And then this has an action by GM, just scaling the coordinates. And if you mod out, you get the projective line, right? And so you just look at this quotient map. And this is called the half map. And this has many wonderful properties. And so, because I mean, there's this stable in my talk title, so I'm going to immediately just stabilize everything, right? So I just do suspension spectra. So there's some induced map here in the Motivic stable homotopy category. And then there's this, this well-known fact that, so P1, this is just sort of the 2,1 suspension of the sphere. And it's also pretty well known that A2 minus the origin, this is, so this is the 1,1 suspension of the 2,1 suspension of the sphere. Right, and so now I can cancel off, I suppose, these 1,1 suspensions. Oops, no, that's not what I'm supposed to do. I'm supposed to cancel off the 2,1 suspensions, right? And so then I obtain some map, which just goes from the 1,1 sphere to just the sphere. And so this we denote by eta. And this is what's called the stable half map. Or maybe instead of stable, or maybe in addition to stable, some people might say geometric, to distinguish it from sort of the thing which just comes from classical topology and which go from the usual one sphere, not the 1,1 sphere. Maybe sometimes called the half element, whatever. So this is the guy which the eta in my title refers to. And then we can immediately formulate what our goal is. The goal is to study the following category. Well, I take the Motivic stable homotopy category over S, and then I want to invert eta. So what this means is just I look at those spectra which think that eta is an isomorphism, right? So this is just the category of all those spectra E, such that the map sort of E smash G, or let me write sigma 1,1 E. It's confusing. Goes to E, right? So this is just induced by eta, and this should be an equivalence, which is a full subcategory of SH of S. And I mean, this inclusion has a left adjoint, so it's a symmetric monoidal localization, yada, yada, yada. But I mean, in principle, you have some spectrum, then there's some universal way of making it eta-periodic, and then I want to tell you as much as I possibly can about this spectrum, like for example, its homotopy groups. So that's the main goal. And right, so I think we've made some good progress on this question, and I will try to give you an idea of some of the main results which we've obtained. And so what I will do is I will try to work my way from general base schemes S to more and more specific ones. Okay, so from the beginning, I have to have one assumption. I need to assume that 2 is invertible on my scheme. So you can use Q or you can use R, but you cannot use the integers. But you could use the integers with the 2 inverted. So there are a bunch of reasons for this. mostly because somehow the way in which 2 and eta interact just in the Grothendieck-Witt ring, the Milner-Witt K-theory, and that sort of stuff. So it's not inconceivable that one might prove analogous results even if 2 is not invertible, but there are sort of several roadblocks. All right. So now I'm going to try and formulate what we can say over general basis, of course. So any scheme containing 1/2. So what's going to happen, or what does happen, is that there exists a certain special spectrum. So little kW, which we call connective Witt K-theory, I suppose. So this is one of your eta-periodic spectra. And it has a bunch of wonderful properties. So first of all, or I don't know, the first thing which came to my mind is that it's a ring spectrum. So it represents a multiplicative cohomology theory, or I mean, it has a multiplication map, and I mean, in fact, it's an E-infinity ring if you care about that sort of thing. Then I mean, there's a special element which is called beta, the so-called Bott element, which lives in pi4 of this guy. And so if you invert this, then you get something well known. So if you take kW and you invert beta, then you just get a thing which is denoted capital KW, right? So this is the usual so-called Witt K-theory spectrum.
Excuse me, did you forget an index in the homotopy group is pi4?
Did I forget what?
Did you forget an index in the homotopy group?
No, I mean, it's eta-periodic, so the second index is always irrelevant. Right, I mean, I think it would live in pi8, 4 maybe, and then I subtracted 4 from both.
All right.
Okay, so this is the spectrum, the Witt K-theory spectrum. So as a cohomology theory on varieties, this represents so-called Balmer-Witt triangular, well, Witt groups. No, yeah, Balmer, yeah. And I mean, there's also a different way of thinking about this, which is you take KO and you invert eta, where this KO guy is the Hermitian K-theory spectrum. Okay, so I'm telling you that there is this special spectrum KW, and I'm trying to get you sort of accustomed to what it does. And well, so there's this one element. If you invert it, then you get something interesting. Then there's a very special map, which you call phi. And so it goes from KW localized at 2 to the fourfold suspension of the same guy. Where this localization at 2 here, it means that you've inverted all the primes other than 2. Actually, it would be enough to invert just 3, but I don't know. For symmetry reasons, it seems more natural to do this. Okay, and so this is related to Adams operations in the following way. Well, so I can start at K with KW and I do my phi operation. So I get into this suspension. And then I'm going to undo somehow the suspension by multiplying by beta. Okay, but so on the other hand, here I could just go to my Witt K-theory spectrum and here also. And what I want to claim is that there's a map which you can put here to make the whole thing commute, and that map should be familiar, and namely the map which you put is psi3 minus 1. And where this psi thing here, right, so this psi guy, this is an Adams operation. Well, on Hermitian K-theory or on Witt K-theory, you can of course periodize it, and you can use the one which were constructed by Jean Facel and Olivier Autillon. So this is the Adams operation. Okay, and also maybe as another point is that all of these structures are stable under base change. Of course, it's the Adams operation and capital KW are stable under base change, and like our allowed category of schemes has a final object, which is the spectrum of Z1/2. This is really just this base change stability is really just saying that everything is defined over Z1/2, and then you just pull back to wherever. But well, okay. Right, and so with this preparation or claims out of the way, I can state our first theorem. So this is maybe the first theorem. I mean, all of them are due to me and Mike, but let's emphasize it. So this is somehow the fundamental thing. So there is a canonical fiber sequence. And what it does, I mean, you can figure out the fiber of this phi guy. And I mean, this whole reason for existence is that the fiber is basically the eta-periodic sphere. Okay, and so then the idea is that hopefully if you know something about this guy and something about this map, you can figure out things about this guy. Let's see. Right, so let me interject a parenthetical remark, which is that why is this localization at 2 here? Well, I mean, A, because that's how we can prove something, but why is this not such a big deal? The point is that if you take SH of S, right, and you inverted eta, and now I've localized at 2, so I need to somehow understand the opposite, so let's invert 2. And then this category is sort of well understood. So this is equivalent to just SH of S red. And I don't want to go into it, but this is basically sheaves of spectra on a certain topological space. And of course, 1/2. And so this is sort of easy. And then the point is that, right, so if you can understand the 2 local case and you can understand the 2 periodic case, when I'm just claiming that the 2 periodic case is somehow easy, then you can often hope to patch together these things to get an integral result. And so we can do this.
Tom and Schuldigen, can I have a quick question, please?
Sure.
Yeah, for example, the right-hand sides are splitting into the plus and minus part. How does each of these look, the right-hand side?
The left-hand side splits into plus and minus part.
Yeah, and if you have an equivalence, doesn't it the right-hand side split?
I mean, this guy splits, right? So this is
yeah, and after inverting
right. I mean, this part, right? So this part is precisely the eta-periodic part. And here eta is 0. So this is if you want the eta complete part. So what this is saying is that this is the minus part.
Ah, okay, this is my question. Okay, thanks.
All right, no problem. So, right, okay. So I was saying that you can try to use this to compute things, but not in the generality, but we can prove an interesting result in the generality of our schemes. Well, with 2 invertible. And it goes as follows. So it has to do with these cobordism spectra. So there's a guy called MSP. So this is an algebraic version of symplectic cobordism. And then you invert it. Well, you invert eta, of course. And then you look at the homotopy groups of this guy. And it turns out that there are certain classes in there, which we call Y1, Y2, and so on and so forth, right? So Y1 lives in pi2 and Y2 lives in pi4 and so on and so forth. And they're maybe not super canonically defined, except of course you can pick them over Z1/2 and then pull them back to everywhere. And what they're going to do is that two things are going to happen. So first, if you mod out by the odd ones, you get MSL. So if you take MSP and you mod out by Y1, Y3, and so on, then you get, well, eta inverse, you get MSL. Right, where this is the so-called SL-cobordism spectrum. And you can keep going, and if you invert, if you mod out all the other generators except for the first one, so you take MSL and you mod out Y4, Y6, and so on, then you get this little KW guy. So that's, I think that's a fun result. So maybe not, I'm not going to write the next parenthetical remark, but remember, right? So I told you that somehow there's the plus part and the minus part, and the plus part in a way is controlled by this guy, and so some sort of computation. The minus part is this thing, which is supposed to be easy, right? So the minus part somehow is real realization, and you can ask yourself for these claims, right? So there's a plus part and a minus part to it, and at least the minus part should be somehow easy. So does this make sense on real points? And I mean, I claim that it does, of course. So how does this go? Well, the real realization of MSP is MU. And you know the homotopy groups of MU is a polynomial ring on generators, well, in even degrees. So that these Y's, they seem pretty reasonable. And well, the real realization of MSL is MSO. And so what this is saying, of course, the real realization is, because it's eta-periodic, it's also going to be 2-periodic, right? So what this is saying is that if you choose your generators FMU 2 inverted in a good way, then if you kill the odd ones, you get MSO with 2 inverted. And if you kill the other ones, you get little KO with 2 inverted. And I mean, I guess this is a well-known result in topology. One can find references for this. So, right, but so you can see that somehow this gets glued together with some 2 primary part, which is more genuinely motivic, and then you get this integral statement here. Okay, so I think these are the most interesting things which we can say over general base schemes. So now we specialize a bit, or dedekind schemes. Right, so what this means, of course, is that, well, what I'm going to mean by this is that S is the spectrum of D, where D is some dedekind domain. Of course, still containing 1/2, so you can take the spectrum of Z1/2, for example. Or, of course, you can take your favorite field of characteristic knot 2. And the point is that then we can say much more about this little KW guy. So this is Theorem 3. Is that, so we had this map from little kW to its beta periodization, which was capital KW, which we sort of think we know. And in general, I don't really know like how the left and right hand side relate. But right, I mean, in classical topology, the little letters always mean connective cover. And it turns out that over a dedekind scheme, this is true. So this is a connective cover. In the homotopy T structure. So over a field, this homotopy T structure is very well known and it's very well behaved. And it just means basically that the homotopy groups or homotopy sheaves of this guy are the same as the ones of this guy, except you cut off all the negative ones. If you're not over a field, unfortunately, the homotopy T structure doesn't work quite this nicely. So there's still a formal way of defining it, but I don't think we have a good expression for what the heart is. And it's certainly only loosely related to the homotopy sheaf. So it's not true in general that sort of cutting off in the homotopy T structure is the same thing as cutting off in the homotopy sheaves. So that's somehow the bad news. But the good news that in this case is everything is fine. So in fact, the homotopy sheaves of the little KW guy, they're exactly what you would think. is the homotopy sheaves of this guy just cut off. So it's just you take this sheaf of Witt rings and you adjoin this generator beta. Right, so this is sheaf associated with the Witt rings. Okay, and so now the point is, once you have this information and you have yourself the fundamental fiber sequence, you can do all manner of computations and you can work out loads of stuff. So there's, for example, the following corollary, which is that we can work out the homotopy sheaves of just the eta-periodic sphere, let's say localized at 2. And you can give an explicit answer. So let me write this out because I think it's quite interesting that we can do this in full. So you get the 2 localized Witt ring if, well, in degree 0. And then basically you get something in positive degrees, either divisible by 4 or congruent to 3 mod 4. You get either the kernel or the co-kernel of some map. So let me try to write this. So you get the co-kernel of this map W2 goes to W2, which is 8n. If you're in degree 4n minus 1, which also should be positive, and you get the kernel of this same map if you're in degree 4n, and you get 0 else. So what should I say about this? Well, one is you have this 2 localization here, but you could remove that if you want. So if you want to remove this 2 here, you just remove this 2 here. And then you have to also add some extra terms. So also in degree 0, you just get the Witt ring, and in positive degrees, you get the sum of this thing here plus something purely coming from the classical. So just the classical stable stem tensor with the Witt sheaf. And this is basically because of Motivic Serre finiteness, which tells you that all the higher degrees are torsion, and then you can just, it's always just the sum of the 2 local and the 2 periodic part. The other thing to say is that lots of people have worked on this problem, this particular problem before. So I think the start was Andrews Miller, who did this over C. And then some work of Yu Isaacson over R, and also of Ormsby-Rundix over many fields. Okay, but we also give a proof of this. In fact, I can prove it for you now. Well, assuming the other facts, right? So you just look at the fundamental fiber sequence. And this gives you a long exact sequence. But this long exact sequence is lots of zeros, right? Because beta was in degree 4. And so the homotopy groups of this is just the Witt ring in degrees 4 divisible, non-negative degrees divisible by 4, and otherwise it's 0. And so this long exact sequence is very, it splits in it's very boring, right? So it tells you that you immediately learn that sort of pi 0 is this Witt guy, and you learn that that the other groups they're given by the kernel and co-kernel of the action of phi, right? So if you think back to this fundamental sequence, right, you're going to see the kernel and the co-kernel of this map phi. This map, so it's going to be something like pi 4 star kw localized at 2 goes via phi to pi 4 star minus 4 kw localized at 2, and we know what these are. We know sort of that abstractly this is just a sheaf of Witt rings. We even know a generator is beta to the n, and this is maybe equal or isomorphic, I don't know, w beta to the n minus 1. And then you have to ask yourself what does phi do to the beta to the n? And if you look at this diagram here, it tells you basically that the way phi operates is you do psi 3 minus 1 and then you divide by beta. And of course, if there's beta torsion, this is a bit iffy, but here's no beta torsion, so it has to be that. So you need to just know what psi 3 does, and well, Fazel-Odion tell you what it does. It's right. So phi of beta to the n is psi 3 of beta to the n minus beta to the n divided by beta. And psi 3 is a ring homomorphism. Psi 3 of beta is 9 beta. So this is 9 to the n minus 1 beta to the n minus 1. So you would think that instead of 8n here, I should write 9 to the n minus 1. But they have the same two-adic valuation, so it doesn't matter. Okay, so that's how you get this complete answer. So I should say maybe, right, so how did I get this? This is from the construction of the Adams operation. Okay, and then you can basically play a similar game with SL-cobordism and SP-cobordism, and the algebra is a bit more involved, but you still get the complete answer. So this is what we call Theorem 4, which is that, right, so we can just work out the homotopy sheaves of MSP, and they're just given by this Witt sheaf, and then you join the obvious generators. And then, of course, the homotopy sheaves of MSL is going to be, you just take your Witt sheaf and you join the even generators. Okay, and now maybe one thing to say. Okay, I think I'm all right with time. So one thing to say is that I always talk about these homotopy sheaves, but maybe that's slightly arcane, right? So the more natural thing is to ask about the homotopy groups. Like, I mean, what are the algebraic cobordism, or what are the symplectic cobordism groups of some like the integers? And of course I don't know, but so the point is that you can often or sometimes deduce these things by this descent spectral sequence. So what you can show is that if, for example, you take Z1/2, then this Witt sheaf is actually acyclic. So this is going to be the Witt ring of Z1/2 if the star is 0 and 0 else. And in fact, you can even work out what this guy here is. This is some small ring, just Z plus Z mod 2 with some explicit multiplication. So this is some very concrete thing. And then you can use the descent spectral sequence. So this is something like you take HP Nisnevich of the sort of, let's say, over X with the Q homotopy sheaf of your guy. And this will converge to pi Q minus P, oops, whatever this is, pi Q minus P of E, sort of over X, right? And now I will take E to be some spectrum which I want, like MSL or MSP, and I take X to be, of course, the spec Z1/2. And then because there's lots of zeros in our homotopy sheaves, and because there's, well, no higher cohomology, you will find this is always degenerates. I mean, for these examples. So this degenerates for X equals spec Z1/2, and E equals something like eta inverse MSP or eta inverse MSL or KW, or even the sphere, eta inverse the sphere, let's say localized to 2. And so therefore what you learn is that, for example, the homotopy groups, not homotopy sheaves, of eta inverse MSP over Z1/2. This is just the Witt ring of Z1/2, which again I said is some explicit guy, which we could write out, and you join these generators. And you can do similar things for the other spectra, and so you get some maybe slightly more concrete thing than this arcane homotopy sheaves business. Okay, so we've done general basis, we've done dedekind schemes. Let me finally give you something over fields, and let me actually call this computational information. So I'm going to say that S equals spec of K a field. So there should be maybe two warnings with this. The first is that lots of what I'm going to say next is also true in one form or another over a dedekind domain. But maybe what I'm trying to say is that it's easier to state over a field, and I don't think it's particularly, well, I don't know. Maybe it's more natural to ask this over fields, but probably true in some other generality. And the other warning is that I'm putting here this word computational, but I should also be very transparent that I don't think I'm a computational person. So I'm going to try to tell you some things, which I hope maybe the computational people among you will find interesting, but I don't really know if this is the right sort of thing to say, so we'll see. So I need to introduce one more player, which is HW, which is basically sort of the replacement for HZ in this eta-periodic context, and I can just define it by taking my little KW and modding out by beta. Note that, I mean, this is basically the Eilenberg-MacLane spectrum on the Witt ring, right? Because the homotopy groups of this guy is just, well, Witt ring adjoint beta. Now a kill of beta, so it's just a Witt ring. Fine. All right, so here's what Theorem 5 is. So it comes in several parts. And I mean, it's just saying it works out some things which I've seen people be interested in. So the first thing which I can do is I can work out what the ring of operations is of this two local connective Witt K-theory guy. So I can work out this thing here. So the cohomology of itself, and then so that makes it sort of a module, and then it has a ring structure coming from composition. And we can work out what this is explicitly. So let me write it first, KW2 star, and then power series ring prime. There's an important prime here, phi. Okay, so what do I mean by this? First of all, as I said, it's a module over KW upper star, which of course we also know is just the Witt ring adjoint beta. And then you have some maps from KW to itself, maybe some degree shifting things. So for example, there's of course phi, and there are also all powers of phi and sums of phi, and it turns out that you can make sense of power series in phi. So that's what it is additively. So it turns out that there's sort of you can form these power series in phi, and they define maps for some slightly miraculous reason. And so what this prime here means is that the composition product is slightly more involved than the power series ring. So in the sense that the composition product well, so what can you do? Well, you can multiply the phi with itself, of course, but that's very boring. You can swap phi's around itself, and it will also commute with everything in the Witt ring, because that's basically coming from the sphere. Everything has to commute with like operations from the sphere. So the only question is, how does phi interact with beta? And so there's a formula which you can work out easily, which is that phi beta is the same thing as 9 beta phi plus 8, apparently. And with this information, you can basically you can write down any map from this KW guy to itself. It must be this sort of power series, and you can compose these guys in any way that you want. Okay. So hopefully this might be interesting. Then another fun observation is that you can try to work out the homology of KW. Localized at 2, everything will be localized at 2. I mean, I don't know, maybe that's something which you're interested in. And so the answer is kind of cool. I'm not sure why this happens, but so what you get is a free divided power algebra. So it's a free divided power algebra over the Witt ring, 2 localized, of course, on a class x in degree 4. So what this means, right? So remember that the sort of a divided power algebra is the sort of thing where you're allowed to take powers, but then the powers can have denominators somehow. So you can present this as follows. You take the Witt ring of K, localized at 2, and then you join your generator X, which I'm going to call X, so the first divided power. And then you have to adjoin somehow more generators corresponding to these higher powers. And then there's going to be some relations, which, well, it's the following. It's xi x j equals I plus j Jews j x I plus j. Right, so if this Witt ring was somehow rational, or if you rationalize the whole thing, then you find that like these higher powers here, they're just some, right? So you find that sort of x higher power n is the same thing as x to the n divided by some number. So if you're allowed to divide, no problem, then you would just get a polynomial ring on this generator here. But because there can be torsion, or I mean, because it's not rational, this is not true, and so somehow the multiplicative structure is more complicated. But certainly, what happens is that this is somehow this is again the Witt ring in all degrees divisible by 4. Right. So if you don't care about the multiplicative structure, then this is just some free module over the Witt ring on 1 x squared, and so on and so forth. Okay. And then maybe for a final computational thing is that we can work out the co-operations of HW, at least additively. I mean, of course, this is some Hopf algebroid or Hopf algebra, I don't know. So there's just more to be known, but additively, I can tell you that it's the sum of Witt rings modulo 8n on this generator, I mean, on these generators. Right, so in degree 0, you get the W, the Witt ring, which of course you knew you had to get. And then in the higher degrees, it turns out that you get these higher and higher torsion groups in degrees divisible by 4. Make of that what you will. Okay, so these are, I know it's a lot, but these are the results which I wanted to mention. And so the rest of my time, I'm going to try and give you some ideas of how the proofs go. I mean, to be honest, I'm not going to give in any reasonable way a full account of how to prove these things, but yeah, so that I call this section idea about proofs, or ideas about proofs. All right. So the first thing is that we go back to this parenthetical remark earlier that if you invert 2, then things are somehow very easy. So what I'm going to explain to you is how to prove results sort of localized at 2. And once you have this, you get these results tensored with Z1/2 easily in some sense. So by reduction to topology. And then you patch them together. So this may or may not be totally trivial. I mean, if you want to show that some map is an isomorphism, then you just have to check it separately. But I mean, for example, if you want these generators of MSP or something like that, you can write them down of tensor, right? You can write them down here. You can write them down here. It's not immediately obvious that you can do this in such a way that they fit together. But I mean, some little more argument, one can somehow fix it. So then I want to observe that this theorem 1 plus 3, right, so remember 1 was the one which says that, I mean, there's this fundamental fiber sequence, and 3 says that over a dedekind domain, the little kw guy, that the homotopy groups are what you think. And this implies the other ones. Well, it implies 2 plus 4. So how do you do this? Well, I've more or less already told you. The point is that you can compute pi star of MSP, eta inverted, and also for MSL and so on and so forth, using the so using the fundamental sequence and basically algebra. Right, I mean, so what you have to know is you have to know what the KW homology of this guy is, but that we know because, I mean, KW is SP oriented, and so then it's just some polynomial ring. And then you have to know how the Adams operation acts, and this is maybe not totally obvious, but okay, you have to find your way through, and then well, you have to figure out the kernel and co-kernel of this map, and I mean, it's a bit hairy, but in principle, you just have to suffer through it and you do it. Okay, and then just the same thing for MSL. And then, of course, this tells you that you can deduce this theorem 2 over dedekind domains. Right, so remember that Theorem 4, it told me what the homotopy groups of MSP are over dedekind domains, and Theorem 2 said something like if you take MSP and you mod out the even generator, the odd generators, you get MSL. Of course, if you know all the homotopy groups, then it's clear that you get this result. So you know it over dedekind domains, but then of course you've proved it over Z1 half, and so you get it everywhere by base change. Okay. So basically we have to concentrate on theorems 1, 3, and 5. And I'm going to do this in 2 steps, which I call A and B. So the step A, and they're basically independent. So step A says that you so that the plan is you construct this little KW guy, you construct phi, and you construct your fundamental sequence, by which I mean, right? So you have this KW2, phi goes to sigma 4 KW2, and then you have my sphere 1, eta inverted localized at 2. So what you do is you construct this map, and you construct a null homotopy here. And you do this over dedekind domains. And also you prove Theorem 3. Right, so whatever you did to construct this little KW guy, you better also tell me that it has the homotopy groups, which I think it does. And then there's step B, which is that you prove Theorem 1 for fields of finite VCD. Maybe 1 plus 5 or something. And so the thing is that if you prove it for fields of finite VCD, you get it for all fields basically by base change, because every field contains a field of finite VCD. VCD2 maybe. And also the thing is that sort of step A is basically trivial over fields, because you just define little kW to be the connective couple of capital KW, and then because the homotopy T structure works well, you know all the homotopy groups, and then constructing this extra data is relatively formal. And so in this sense, basically there are 2 completely independent problems. One is that you get the whole thing going somehow over fields, and the other is that somehow you have to construct your data over dedekind domains, which is much more complicated. And then the point is that once you have the sequence here, you get a map from the sphere into the fiber of phi, and you want to know that this is an equivalence. But if you want to check this, let's say over Z1 half, it's a theorem that you only need to check it on the residue fields. So these all have finite VCD, and so you're reduced to this step B thing. And so then you learn that this is an isomorph, I mean, right? So this is exact over Z1 half, and then by base change it's exact everywhere, and then you're done. So basically that's the plan. And so what I'm going to try and do is I'm going to try and say something about step A, And then I'm saying a little less about step B, and then the time is probably going to be over. Right, so how do we do step A? Well, we have to construct this little KW guy. And I mean, of course, the point is that the theorem theorem, whatever, 3, it says that it's the connective cover of capital KW. And so I can just define it to be that. But the problem is that then I have no control. I don't know what its homotopy groups are. I don't know that it's stable under base change. So that seems a bit of a problem. So I'm going to do something else. And so this ties in with the lecture series of Mark Oyowa a while back. So I want to recall this sort of frame spectrum technology. So there is this category of so-called motivic spaces with frame transfers. And I mean, there's lots of names associated with this, but let me just put the gang here. So that's Almanto, Oyowa, Kansos, Nido, Jakobsen, who certainly, they put this frame technology into a sort of a nice infinity categorical framework, and they made it all very functorial and everything. And so what you can do is, out of these spaces with frame transfers, you can build spectra with frame transfers. So this is called SH framed of S. And then there's this adjunction between them, sigma infinity framed and omega infinity framed. And so the point is that you can forget to frame, I mean, spectra with no frames, well, without transfers. So you just forget to ordinary spectra. And this is an equivalence. So this is due to Mark Oyowa. And what this tells you, or I mean, one of the things which this tells you is that you can use these spaces with frame transfers as a convenient way for constructing spectra by taking so-called framed suspension spectra, right? I mean, just do this thing. And I'm going to do that for reasons which hopefully will become clear. So what I want to consider is I do this omega infinity framed of KO. Right, so KO certainly lives in here, and so under this equivalence, I can move it to here, and then I'm delooping it to here. So this is going to be a framed space. But the point is, and I'm going to denote it by GW. And I mean, why is that? Because, well, KO represents Hermitian K-theory. And so what this means is this is some framed presheaf whose underlying presheaf is, well, the presheaf of Grothendieck Witt spaces, and then it has some frame structure. Who knows how that works? Well, you can work out how it works, but it encodes a lot of extra structure. And we know that the underlying motivic space is given by this sort of orthogonal Grassmannian. This is due to Marco Schlichting and someone. And so the point is this guy is stable under base change. So the underlying space with transfers forgotten is stable under base change, right? Because Grassmannians are. And then this implies that this the space with transfers is also stable under base change because the base change of frame spaces commutes with this underlying functor due to Mark Oyowa. Okay, so now I can give you the definition, which is that I will say little kW is just, you take the frame suspension spectrum of this GW guy and you invert eta. Okay, and so by construction, this is stable under base change, but we know very little else right now, I suppose. But so I can construct some elements in the homotopy groups. So there's some beta in pi 8,4 GW. I mean, simply because, I mean, there's some beta in pi 8,4 of KO. And I will use this to define the beta, which I talked at the very beginning. And on the other hand, there's also beta and eta in pi 1, 1 of GW. Again, simply because there's an eta in pi 1, 1 of KO. But of course, there's already an eta in pi 1, 1 of KW because, well, eta comes from the sphere, right? But this is the same. So this is the honest eta. So that's not obvious. And I mean, let me just call this framed magic. I mean, it's less magical if you remember that over a perfect field, this functor here is basically just a group completion. So it's fully faithful on group-like objects, right? So there was an eta here, and so there had to be an eta in my GW because it was because it is group-like. And so over a general base, this argument doesn't work, but you can still check that this eta somehow it suspends the correct thing. And now I can use an interesting trick, which is so if I do this, take this frame suspension spectrum of GW, and I invert beta, right? So this is some guy which exists already in the homotopy of sort of the space, the frame space, and which lives in degree 8,4. And then there's always the fact that you can represent this mapping telescope or this spectrum here as a periodic spectrum. As a, well, S84 periodic spectrum. Right, so what I mean by this is just you take the space GW, that's your first space, and then you take the space GW, which is your second space, and also your third space, and so on and so forth. And all the bonding maps are beta. And if you unwind what this means, you just basically get this guy. But you see, this spectrum is basically, I mean, this sequence of spaces is basically the definition of KO. And so what you've learned is that if I take my KW and then I invert beta, so that's the same thing as KO with eta inverted, which is KW, which is what we wanted, right? So we're sort of beginning to see that this guy does what it should do. And similarly, I can, right? So I've defined my little KW to be obtained by eta-periodization. And so we can try to play the same game here. But the issue is that eta is in degree 1, 1, right? So I can only build a GM spectrum. So what this means is I have to S1 suspend it first. So similarly, sigma infinity framed GW, if I invert eta, so this is modeled by the periodic S11 spectrum. So with bonding maps eta. Right, so what I mean by this is that instead of sort of doing framed motivic spaces, you do framed motivic spectra. So I mean, by which I mean sheaves of spectra with frame transfers, so framed motivic S1 spectra. You can put them in the middle here. So you first have to apply this functor, figure out what you get here, and then you have this periodization procedure. And so what this tells you that the homotopy groups basically the colimit of n-fold GM loops on this, well, let me just write this somehow this spectrum GW greater than or equal to 0, which is in fact W adjoint beta. So let me say that I'm lying, or I mean, I'm lying by omission a little bit here, which is that one thing which you need to know, right? I mean, basically what I've done is I've computed this S1 spectrum. I mean, this S1 suspension spectrum. And in order to, and this is not particularly hard because you basically already have this group-like E-infinity space, so S1 suspension shouldn't do a whole lot. But what you had to know in order for this to work is that this sheaf of Witt rings is actually strictly homotopy invariant on it over this sort of dedekind, I mean, right? So on smooth schemes over a dedekind domain. You of course deduce this also from this result, right? Because if I take a cofiber of beta, I have just this Witt ring sheaf, and of course it now has to be strictly homotopy invariant. But it turns out you actually need to feed this in. But luckily enough, one can get this relatively cheaply by combining certain results of Marcus Spitzweg and Jeremy Jacobson. And now basically you've proved theorem, well, half of theorem 3, and it turns out that the rest is relatively formal. Okay, so now in the last 3 minutes, let me say a little bit about step 4, step B. And let me also say that in a couple of weeks, I'm speaking at the electronic computational homotopy theory seminar. And I think my talk is mostly going to be about step B, because I think it's maybe more appropriate there. But so what do we need to do, right? So we need to somehow show that this fiber sequence, well, that this sequence is a fiber sequence. So you need to somehow work out, where are we? Here. Right, so somehow you need to work out that the fiber of this map is this guy. And I mean, there are various things which you can try. One natural thing I feel is you try to do this in homology, right? So I smash this with HW here. And then certainly what I need to do is I need to know what the homology of this guy is. There are other things which you can do, like related, you can try to do some slicing, like Oliver and Kyle did, but okay. So one possible starting point is that you try to understand the homotopy groups of this guy, HW smash KW. And also, I mean, we only need to sort of 2 locally. And in fact, if you invert 2, again, it's easy, right? So I can just as well also complete it at 2. But I mean, so then you run into a fundamental problem is how do you work out anything in Motivic stable, or I mean, how do you work out anything in homotopy theory at all in general, right? And so basically, well, what do I know? But the typical ways are sort of you do some sort of descent thing from homology to homotopy, so you run some spectral sequence. And the fundamental problem is that all the spectral sequences we usually use in Motivic homotopy theory, they converge to some sort of eta completion. In particular, if you try to do this on an eta-periodic guy like this, it's never going to work, right? So you can try to run the Motivic Adam spectral sequence, but it's not going to tell you anything because, well, it's just 0 everywhere. And so then the technical input which makes the thing work is the following theorem due to myself and Elgin and Paul, which says that some things are somehow miraculously eta complete. If the VCT2 of k is less than 0, or less than infinity, less than 0 is maybe unlikely, and the characteristic of k is not 2, and E is a very effective spectrum, then somehow the 2-adic completion is eta complete, even though, I mean, a priori doesn't have any right to be. And so a related thing is that you could try to use the slice filtration, but then you would ask if your guys are slice complete. And then there's a theorem related to this thing here, which tells you that again, if your VCD2, if your virtual 2 Italian cohomological dimension is finite, if you don't have characteristic 2, then any connective spectrum mod 2, well, eta-periodic connective spectrum mod 2 to be safe, is slice complete. So then you could also do a slice argument. But again, there's sort of the same wall, and you need this you need this kind of result to break through it, I think. So now if you have this, then you can do the following thing. So what I'm gonna do, the strategy is to do some sort of eta complete computation and then invert eta and to somehow deduce this. So I need to first sort of replace these spectra here by some very effective analogs. And so I'm gonna, well, so maybe I should do it the other way around. Right, so I'm gonna replace little HW by something called K upper W. So this is the so-called unramified Witt K-theory sheaf. Doesn't matter right now what it is. And I'm replacing little kw by little ko. And now let me complete the set eta. Right, so this is maybe something which you could believe that you can compute something about. Now I'm inverting eta. And then I'm completing it too. And so again, you could believe that you can compute something about this guy, right? But so I can add, right? So there's the eta completion outside, so I can also move it to the inside. And in addition, so this is the same thing as kw smash ko eta completed, also 2 completed, eta inverted 2 completed, and then, well, by the theorem above, I mean, you need to know that these guys here are very effective, but let's grant this. Then you know that you can remove the 2-adic completion, the eta-adic completion, right? Because it was already eta complete. But now I'm completing on the outside again, so I can just remove the whole thing, right? And now I just move the eta-periodization on the inside, and I get, well, HW smash KW 2-adically completed. So now we've computed the guy that we wanted. And I mean, of course, you still have to do it. And it took me a while to figure out how to do it, but this is at least sort of why it's possible to do it. Right, and then you can fight that work. And maybe this is all I can say in my -2 minutes.
Okay, Tom, thanks a lot for a beautiful talk. Now we can all unmute and give Tom a well-deserved round of applause. Okay, let me ask the first question. This at the very end here, there's a little KO. Can you explain to us what this is?
You mean what is little KO?
Yeah. Did you define that?
Sure. I mean, I can define little KO as the very effective cover of capital KO. It's also the same thing. I mean, I'm working only over fields here, right? It's also the same thing as the framed suspension spectrum of this GW guy. So this was studied, for example, in this paper by Ananievsky, Roendex, some other people, something like on very effective Hermitian K-theory. But that's what it is. Does it answer your question?
Yeah, great. Okay, maybe there are other questions. Just go ahead, folks.
What is the capital K, upper capital W in your last theorem?
Right. So I mean, it's not in the theorem, but it's used. So this capital, yeah. So this is some technical guy, but capital K. This is the same thing as pi 0 of right. So this is the homotopy sheaf of Milner-Witt K-theory. And then you divide by this element h, where h is sort of the hyperbolic plane 1 plus -1. So this is some technical guy, and one can prove that it's very effective. So it's some sort of Einberg-MacLane spectrum. It's a bit surprising that this is sort of reasonable, but in particular, I mean, you see that, right? So the sheaves in here, they're given sort of in negative degrees by the Witt rings and in positive degrees by the powers of the fundamental ideal. In particular, if you invert eta, you just get Witt rings, so you get this guy. Does that answer your question?
So I have a question.
can you compute the cohomology of project space or project bundles for your eta-periodic spectrum?
I mean, I don't think that I have anything particularly interesting to say about this. So there is some work by Ananievsky about this. And I mean, one thing to say is that there are lots and lots of curious things going on in the eta-periodic setting, which I haven't said here, and also which I don't really know what they're good for. So Mike probably would have a better answer for this. But for example, there's this sort of equivalence that KW is it's MSL3. So the answer is I cannot, but it's not inconceivable that something interesting can be said.
Okay, thanks. Okay, thanks.
Okay, any other questions? Last chance.
May I ask a question? You said you use strict homotopy invariance for Witt spectrum, and you refer to result by Spitzweg. So you use both, or there are two possibilities? Can you explain again? You need both results, or there is a choice what to use?
Where
So you mentioned it. You mentioned about that you used the base is the dedekind domain because you need the result by Spitzweg for. So okay, yes.
You want me to say why I need two to be invertible, or?
Why you need that the base is the dedekind domain? This place.
Ah, right. So how? Yes. So it might be that these results hold homogeneity. Yeah. So why? Yes. Let's see. What am I trying to say? Right. So I mean, I guess in the way I presented it in the talk, what I'm using is that this W guy here, right? So this is maybe this Nevitz sheaf on smooth D. And I guess the way I've presented it, the only thing which I need to know is that this has homotopy invariant cohomology, right? So then right, so the cohomology of x times a1 coefficient in W is the same thing as, and the way I get this is sort of by relating this to the cohomology of whatever with coefficients in, let me write this, mod 2 Milner K-theory, by which I mean HZ modulo 2 and tau, right? And so Spitzweg has constructed the well-behaved Motivic cohomology spectrum over dedekind domains. In particular, if I look at its pi 0, I get this, whatever this means here. And so it has to be homotopy invariant. Yes, so this is where it comes from. It's not inconceivable to me that one might do it more generally, but probably with more effort. And also, I mean, maybe it's false.
Oh, okay. Thank you.
No worries.
So it is only one place where you use this assumption on the base, and another place you use another assumption in the invertibility of 2. So for assumption dedekind, it is only one.
Sorry, can you say that again?
So this is only one place where you use assumption that it is the dedekind domain, and another assumption for the inverting of 2, it is another place.
Right. So we have this 1/2 in S. So this is used for a variety of reasons, but I mean, it starts with this thing, right? So this SH of S 1/2. This is the same thing as SH of S 1/2 1 over eta times SH of S sort of 1/2 eta complete, like this, okay? And so what this means is that my eta-periodic, and I mean, this guy we understand. And so what this means is that my right, so eta-periodic problem. So it reduces to this SH of S ret 1/2 and a two local problem or two complete problem. Right, and how can you attack some sort of two complete problem? Well, we're going to attack it basically via something like Adams spectral sequence mod 2, right? So something like HC mod 2. And then you're going to enter the Steenrod algebra. So the Steenrod algebra HC mod 2 star star HC mod 2 enters. And basically we don't know this at the character, right? So I mean 2 is not relevant here. HC mod, we know the Motivic Steenrod algebra, we don't know it at the characteristic. So I think this is fundamentally sort of where it comes from. We have this trick where all primes other than 2 are somehow not relevant. And then usually you would always have the problem that sort of the P complete problem can only be done if P is invertible in your base. Not always, but very often. And somehow only 2 enters here.
Thank you. I understand.
My pleasure.
Okay, any other questions? Doesn't seem to be the case, so I think that wraps up this talk. So let's thank Tom once again for a beautiful talk.
Thank you.